This next section, 3.2, we're going to think of the derivative actually as a function, okay, not just the slope of the tangent line at a certain point. Okay, so let's go back over here to our notes. Okay, so the derivative as a function. Okay, so now when we say derivative, we're thinking of the derivative. This is a different function. It is a function that's going to produce the slope of the tangent line at a particular point. Okay, so the derivative of f is the function. All right, so here again is the definition. So you just got the limit as h approaches 0, and rather than having a this time, where a was the x that we were looking at, we're just going to put in x. So you've got f of x plus h minus f of x, that's difference of the y's, divided by the difference of the x's, which x plus h minus x will just gives you h at the bottom, okay? The derivative of the function is that, provided the limit exists and x is in the domain of f. If f prime exists, we say that f is differentiable at x. If f is differentiable at every point of an interval I, of an open interval I, we say that f is differentiable on I. Okay. Another little picture here. All right, so again, the slope of the tangent line is the instantaneous rate of change. It is the derivative at a. All right. In this case, that slope, if you think about that line, what would the sign of the slope be? Greater than 0, it is positive. Right? Here, that line, the slope would be negative. What would the slope be right up here on the top?
0.
0. All right, so that's a horizontal tangent. Okay. All right, questions about that? Okay, different notation for derivative. And they've thrown a bunch of that at you here in the book. All right, so the prime symbol, f prime or f prime at x, we use that a lot, you know. Another one that we do use is this dy dx. All right, and we'll talk about really what that means a little more when we get toward the end of chapter 4. I'll talk about differentials. But that dy dx, that is just the change in y divided by the change in x along the tangent line is what that actually is. But it's the derivative of y with respect to x is what dy dx is. All right. So again, this f prime of x and dy dx, that's what we use normally. That is really just the limit of the change in y divided by the change in x, delta y divided by delta x, as the change in x approaches 0, as delta x approaches 0. So that's really what dy dx is. Okay. This, we'll see occasionally, this is just saying I'm taking the derivative with respect to x of the function. Okay. I don't think we use this. This means the same thing. This is a notation that we'll see later. I'm not sure if this text will use this much, but this is, rather than saying f of x, it just says y prime of x. If you take differential equations, at some point they use that notation a lot in there, in other places. But I don't know that in calculus, the regular calculus sequence, we use that notation that much. All right, I never use this. Okay, I don't know, with a book might, but we'll see. But anyway, any questions about any of that? Anytime some notation thing comes up, I'll say what it means, but if you do have questions, just let me know. All right, so here's another graph. Same kind of thing. You've got the secant lines, and then when they get closer and closer here to the actual tangent line, you find that as the limit of delta x approaches 0 of the change in y over the change in x, and that gives you dy dx. Okay? All right, any questions? Okay, now here's one type of problem. I've never seen this in other calculus before, I don't think, but it's kind of interesting. All right, so it says sketch the graph of G prime using the graph of G. Okay, so if you have that graph G and you want to graph the derivative of G, that function, okay, just looking at that, what would you do? Okay, now again, we never do that really that much, but what would I be looking at? Okay, so like here I've just got g of x. All right, y is equal to g of x. Okay, I'm going to also graph on there y is equal to g prime of x. Okay, so what is g prime of x? What is that?
The derivative of x.
The derivative of x. What is the derivative of x? So what are you finding when you find if I say the derivative at 2, what am I actually finding? What did we find over there a while ago when we plugged a value in? The slope of the tangent line at that value, right? So the derivative is the slope of the tangent line at a certain value, okay? So if you look at this function, so like if I say I'm here at negative 3.5, and I go up here. All right, well, what is the slope of that tangent line there? What does it look like? Is it positive or negative? Positive, all right? I just kind of have to estimate, all right? But it is positive. If I'm at negative 3, what is the slope of the tangent line at negative 3? Does it look like?
0.
Looks like 0, okay? So that means at negative 3, the derivative of x would be 0, okay? It looks like at negative 1, the slope of the tangent line is what? Looks like it's 0. At 1, it looks like it's 0. Okay, so what they've done first is they've noticed that. So on the graph of g prime of x, you would have a dot. The function value there, the derivative value is 0. So it crosses at negative 3, negative 1, and 1. Okay, does that make sense? Then they notice over here that on this interval here, from here to here up to negative 3, your slope is positive, right? So that means it's going to be above the x-axis. As it gets closer, because that's pretty steep, as it gets closer here, what happens to that slope?
It levels off and it starts going down.
It gets closer and closer to 0, so it's going down. So notice what's happening here. When they graph it, your y values are higher. As it gets closer to negative 3, where it's 0, the y values are getting smaller and smaller. Everybody see that? And then when we go from negative 3 to negative 1, the slope, what's true about the slope there? Positive or negative?
Negative.
Negative. Right. It's negative until we get down to here. So down here, what's happening? It's negative, it's below when y is negative, but it gets lower, and then as it gets closer to this 0 here, it starts getting higher, right? And then from negative 1 to 1, it's going back up positive until it gets closer to that 0 again. So it goes up and back down, and then past 1, the slope is negative, and it gets sharper and sharper and sharper as it goes down. So the graph there goes down, down, down. All right? Does that kind of make sense? We really don't do that much, okay? Because normally we say the functions don't go together, and they don't. But if you were to graph the derivative of g of x, that's kind of what it would look like, and that's why, okay? Any questions about that? All right, let's see. Okay, a few theorems here, and these are very important. All right. Differentiable implies continuous. Okay, now notice it says if f is differentiable at a, then f is continuous at a. So we talked about continuity before, right? How that if the graph is continuous or not. If it is differentiable, then it is continuous. Does that mean that if it is continuous, that it is differentiable? Okay, and not if-then statements do not work that way. All right, so if-then statements are only true when that if the first one is true, then the second one is true as well. But you cannot reverse them. If it's an if and only if statement, then they work both ways. This does not. Okay, so if it is differentiable, then it is continuous. But if it is continuous, that does not mean that it's differentiable. Okay, does everybody follow? Get that? That's very important. If it's differentiable, it is continuous. But if it is continuous, it is not necessarily differentiable everywhere. Okay, we'll see in a minute where it's not. All right, this is an alternate version. This is called a contrapositive, I think. You remember that from high school? You heard that before? All right. If you reverse the if and the then statements and you negate them, then you get another statement that's true. You ever heard of that before? Is that blank stares? All right, sorry. All right, that's contrapositive. Contrapositives are always true. So if differentiable, then continuous, then I can say if not continuous, then not differentiable. That is true. All right, so if a function is not continuous at a point, then it's definitely not differentiable at the point. Okay? Questions about that? Now we'll see examples in just a minute. So, okay. When you took high school geometry, you should have talked about a contrapositive. All right. But y'all don't remember that? You forget things, don't you? All right. When is a function not differentiable at a point? Okay, we've got three different diagrams here that show when a function is not differentiable at a certain point. F is not continuous at A. All right, so if, like on this first graph here, at A, notice it is not continuous here at A because the graph, the y jumps from here up to here. So we will say that is not differentiable at A. It is also not continuous at A. So remember, if a function is not continuous, then we know that it's also not differentiable. Okay, F has a corner at A. All right, so that would be the second example here. So notice how the function here, which is the curve that's in black, when it gets here, it's got a sharp curve that turns down. Okay, so at that point where it takes a sharp turn, that would not be differentiable at that point. Okay, because the slope of the tangent coming from the left is not the same as the slope of the tangent coming from the right. So that would not be differentiable there at A. Okay, the third way that a function is not differentiable is if it has a vertical tangent at A. Alright, so if the slope would be undefined. Okay, so here's an example here where this would be like the well, either y equals root absolute value x, or if you had y equals x to 2/3 power would be the same type thing. You would have a vertical tangent here at this turn. So the slope would not be defined, so it is not differentiable there. If you take the derivative at that point, you would see that when you plug 0 in, then the slope would be undefined. And then here is also an example of a vertical tangent where it would not be differentiable at 0. Now everywhere else on the graph it would be differentiable, but just not at 0 where that vertical tangent line is at. Alright, let's look at this problem. Match the graphs of A through D, so lowercase a through D, of functions with graphs capital A through C of their derivatives. So this graph has got functions, this graph has got derivatives. Okay, and the first thing I would notice is all these functions are just lines. Okay, so remember we said before that the slope of the tangent line of a line is just the slope of that line. Okay, so here I would say, well, I'd look at A. Well, if looking at A, it has a slope, it looks like, if I go from here to here, it looks like it has a slope of up 1/1, so it has a slope of 1. So the derivative of any point on that line A would be 1, which would be y equals 1 is the graph here, which is C. So A, capital A, would be, or lowercase a, graph A, would be C. All right. Notice B, if I look at this point and this one, it looks parallel to this graph of A, and looks like you go up 1 over 1 as well for it. I guess 1's about there. So it looks like we go up 1 over 1, so the slope is also 1 for graph B. So that would also match the derivative graph capital C. So graph B would also be C. Okay. Graphs lowercase c. Alright. Let's say this looks like we're going from here to here. So the slope, I would go down 1 and to the right 1. So it has a slope of -1. Well, y equals -1 over here, and the derivatives is a. And then the graph lowercase d has a slope. If I take this point and this one, the slope is up 1 over 2. So I have a slope of 1/2. Well, that would be the line y equals 1/2, which is B. Okay. This says reproduce the graph of f and then sketch a graph of f prime on the same axis. Alright, well, I'm not going to reproduce it, but I will graph a graph of f prime. I could probably do it on, let's just do it on this axis right here. Okay, that's already there. Okay, if I can draw. Alright, so notice from when x is from -infinity up till we get to -2. So everything back here, the slope of this line is down 1 over 1, is -1. So the slope of the tangent line from -infinity to -2 of that line there would be y equals -1. So let's see, let me erase this where I've do that a little better. So that's just going to be the line y equals -1. So that would be from here over like that. And then from -2 to 0, the slope looks like it's up 1 over 1, up 1 over 1. So that would be the line 1. So that would be from here to here. Okay. I'm sorry, just to 0. Okay, so really just that. And then from 0 to 2, then the slope would be down 1 over 1. So the slope would be a -1. So now we would go back to here, from here to here. And then from 2 to positive infinity on the x, the slope looks like it's up 1 and then over 3. So around 1/3. So I would say that would be somewhere around there. And then it would go that way. Alright. Alright, this one says use the graph of f in the figure to do the following. A, find the values of x in -2, the interval -2 to 2, at which f is not continuous. Okay, so it is not continuous at 1 because you've got a hole in the graph there and that point is removed and is up here above it. So it is not continuous at 1. It is continuous at this curve though, but not at 1. So I would say f is not continuous at x equals 1. And then b, find the values of x in -2, 2, at which f is not differentiable. Okay, well, one thing that we said before was that if a function is not continuous at a point, then it is also not differentiable at the point. So I know since it is not continuous at 1, then it is also not differentiable at 1. So I would say f is not differentiable at x equals 1. Also, you've got a sharp curve here. Okay, so anywhere you have the sharp curve like that, or it's not smooth, then it's not differentiable, and that would be at 0. So on this one, we'd also say it is not differentiable at x equals 0. All right. Use limits to find the derivative of the function of the function f prime for the following function. Evaluate f prime at a for the given values of a. Alright, so we want to use the limit definition and we're actually going to find a derivative function this time. We're not just going to find the derivative at a point. We're going to actually find a function that actually produces the slope of the tangent line. Alright, so my definition is f prime x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Alright, and what you might want to do is go up here and we've already got f of x right there, so what is f of x plus h? Well, that's going to be x plus h in the place of x. Okay, so this would go right there where f of x plus h is. This would go where f of x is. I'm going to go ahead and just write those in. So I'll have 4x plus h squared plus 1 minus, I need to use parentheses, 4x squared plus 1. All divided by h. Alright, so now let's do a little algebra here and see what happens. So if I square x plus h, that's a binomial, so I'll need to write x plus h out twice and then FOIL it out. And I would get this. So xh plus xh in the middle would give me 2xh. So I would have 4 times, tell you what, let me write that up there. I'll save a step here. So that means this is x squared plus 2xh plus h squared. So that's what x plus h squared is. So let's multiply this by 4 now. So I would have 4x squared plus 8xh plus 4h squared, and then I would have plus 1, and then minus 4x squared, and then minus 1 over h. Okay. Now notice some of these subtract off. 4x squared minus 4x squared, that subtracts off. 1 minus 1, that subtracts off. So I'm left with, on the top, 8xh plus 4h squared. Factor out an h. So I'll have h times 8x plus 4h over h. So now, now the h's will divide off since I've got multiplication right there. So I'm left with the limit of, as h approaches 0, of 8x plus 4h. Now I can just plug in the 0, and that will get me 8x. So f prime is equal to 8x. So the derivative function for this function is 8x. So 8x produces the slope of the tangent line for any point on that function. Okay. Now it did ask in the problem to evaluate the derivative at 2 and 4. So if I just take the derivative and I plug in 2, I'll just say 8 times 2, so that would be 16. And then if I plug in 4, I'll have 8 times 4. That'll be 32. So the slope of the tangent line at 2 for this function is 16. The slope of the tangent line at 4 of that function is 32. Okay, this says find the derivative function and then find an equation of the tangent line to the graph of the function. So we've got about 3 of these that we'll look at. Alright, so we're going to use the limit definition again. So remember, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so again, it might be helpful to go ahead and write down what f of x plus h is. It's just this function with x plus h in the place of the x's. Okay, so let's fill that in here. So for f of x plus h, I'll have 3x plus h squared plus 2 times x plus h minus 10. Then I'm going to subtract from that f of x, which is 3x squared plus 2x minus 10. Okay, so now I've got the limit as h approaches 0. Alright, so x plus h squared, remember from the last problem we said is x squared plus 2xh plus h squared. So I'm going to multiply 3 times that and I will get 3x squared plus 6xh plus 3h squared. And then here if I distribute, I get 2x plus 2h minus 10, and then distribute here, I get this all over h, and then we're just about there. Okay, so now the 3x squares will subtract off, the 2x's will subtract off, the 10's will subtract off. Okay, so I'm left with 6xh plus 3h squared plus 2h. And so I can take that and I can factor out an h. So I get 6x plus 3h plus 2. And then my h's cancel, so I'm left with the limit as h approaches 0 of 6x plus 3h plus 2, and then I can plug in h for 0 and I get something that is defined, and so I would get 6x plus 0 plus 2, so the derivative function is 6x plus 2. Alright, now the a value they gave us was 1, so we want to know what is the equation of the tangent line when x is 1. Okay, so to do that I will need to know a point on the line and the slope. Well, the derivative will tell us the slope, so f prime at 1, if I plug that in for x, 6 plus 2 is 8, so my derivative is 8, so that goes there where m is at. And then for x1, y1, I just need to know what the point is there. So I just take 1 and plug that back into the function. So this will be 3 plus 2 minus 10. So 5 minus 2 is negative 5. So it looks like the point 1, negative 5 is what's on the graph. So here I would say x minus 1, y minus negative 5 would be plus 5. And then just do a little algebra here. And the equation of the tangent line at the point 1, negative 5 is y equals 8x minus 13. All right, let's look at another one. Okay, so again, we're going to find the function for the derivative. So it's the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so we will have f of x plus h. So just plug x plus h in for x into this f function. So that would be the square root of 3 times x plus h plus 1. And then minus the square root of 3x plus 1, which is f of x over h. Okay. Well, here we've got a limit with radicals in it. So what we do normally, multiply the top and bottom by its conjugate. So I would say we'll multiply the top and bottom by same thing, except I'm going to change the sign in the middle to a plus over itself. Okay, so this will give me the limit as h approaches 0 of. So now these are conjugates, so all I got to do is multiply the first two and the last two. The middle term cancels out, so that just really just gets all the radicals to go away. So let me go ahead and distribute that out. So I'll have 3x plus 3h plus 1. So that's multiplying the first two radicals. Now I've got a negative times a positive, so that's a negative. And then root 3x plus 1 times root 3x plus 1 is just 3x plus 1 over h times, and I'm going to leave the other under the radical there, 3x plus 3h plus 1, and then plus radical 3x plus 1. Okay. Now, notice what happens here. Okay. If I distribute the minus 1 here to 3x and 1, I get negative. I get minus 3x and a minus 1. So 3x minus 3x is 0. 1 minus 1 is 0. So all I have left on the top is 3h, and then that h will divide out with that one on the bottom. So what I'm left with then is the limit as h approaches 0 of 3h over h times root 3x plus 3h plus 1 plus the square root of 3x plus 1. And then the h's will cancel. So I'm left with 3 over that. And then now I can plug in 0 in the place of the h. So I would get root 3x plus 1 plus root 3x plus 1, which would give me 2 root 3x plus 1. So that derivative function would be 3 over 2 times root 3x plus 1. Okay, so that would be my derivative function. Okay. Now, a is 8, so the point that I would be looking at if I plug 8 in the place of x, 3 times 8 is 24 plus 1 would be 25. Root 25 is 5. So 8, 5 would be the point that I'm looking at on the graph. And then the derivative at 8 would be 3 over 2 times root 3 times 8 plus 1. Well, 3 times 8 again is 24 plus 1 is 25. Root 25 is 5. 5 times 2 is 10. So my slope would be 3 over 10. Okay, so with that, to find the equation of the tangent line at that point, I do point slope form. And then I just distribute that out. Let's see, that'll be 5, 4, well, 24 tenths, so 12 fifths. And then add 5. And that'll be y equals 3 tenths x plus 13 fifths. All right, we got one more. Okay, so we want to find the derivative function first. Okay, so we're going to take the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so f of x plus h would be 2 over three times x plus h plus 1. So let's write 2 over 3x plus 3h plus 1 minus 2 over 3x plus 1 over h. Okay, now you've got a fraction inside a fraction, so always, to get rid of that of the fraction that's inside there, multiply the top and bottom by the least common denominator. Okay, now in this case, 3x plus 3h plus 1 is in no way the same as 3x plus 1. So you've got to multiply by 3x plus 3h plus 1 times 3x plus 1. I barely fit that in on the top and the bottom. Okay, so that will give me the limit as h approaches 0 of, so when I multiply this by this first fraction, the 3x plus 3h plus 1's cancel, so I get 2 times 3x plus 1, and then minus, then when I multiply this times this one, the 3x plus 1's cancel, and I get 2 times 3x plus 3h plus 1 over h times 3x plus 3h plus 1 times 3x plus 1. Okay, so I would leave the bottom like it is, and let's take the top now and see what we can do up here on the top. So I'll have 6x plus 2 and then minus 6x minus 6h minus 2 over h, 3x plus 3h plus 1, 3x plus 1. Alright, so notice now the 6x's subtract off and the 2 subtract off. So I'm left with negative 6h over h times 3x plus 3h plus 1 times 3x plus 1. So now that all I've got on the top is just 6 times h, that h on the top will divide out with the h that's on the bottom. So what I end up with here then is the limit as h approaches 0 of negative 6h over h times 3x plus 3h plus 1 times 3x plus 1. H is canceled, so I just have that. That I can plug in 0 in the place of h. And then I get 3x plus 1 times 3x plus 1. So let's write the derivative as negative 6 over 3x plus 1 squared. That would be f prime of x. Okay. Now the point that they gave us was negative 1. So if I take the function value and I put in negative 1 for the x value, I'd have 2 over 3 times negative 1 plus 1. So that would be 2 over negative 2, which is negative 1 also. So my point where I'm wanting to find the equation of the tangent line is at negative 1, negative 1. Okay. So now let's find the slope at negative 1 and see what that is. So I plug that into the derivative. Alright, so that'll be negative 3 plus 1 is negative 2. Negative 2 squared is 4. Negative 6 over 4 would be negative 3 over 2. So the slope of the tangent line of that function at the point negative 1 is negative 3 over 2. So if I start with my point slope form, then I'll say y minus the y coordinate negative 1, so that'll be plus 1, equals the slope negative 3 over 2 times x minus the x coordinate. In the little algebra there, that will reduce to be y equals negative 3 over 2x. And then if you'll have minus 3 over 2 minus 1, so that'll be minus 5 over 2. Alright. Last problem. Alright. A, B, C. Alright, A says at which points is the slope of the curve negative? Okay. Well, C. Alright, this would be the kind of what the line would look like, tangent there at C. And that is definitely down. You have to go down and over to get the slope. So that's definitely negative. This one looks like it's going like this. That one I would say is negative as well. So C and D would both be negative. Okay. Which points is the slope positive? Well, A, B, and I would say even E is positive, just a little bit. So A, B, E. Okay. Then it says list the slopes in decreasing order, so the largest to the smallest. Alright, so the largest would be positive, and your steepest line looks like it would be A, and it looks like B would be the next steepest, and then E is barely positive. So I would say A, B, E, and then C and D are negative. It looks like C is steeper than D, so I would say D and then C. And that's all.